So this is the plan for today. Last time we were talking about wavelet transform, and the lecture before was about short time Fourier transform. Both transforms have time and frequency axis in its result, in its spectrum. So why we need filter banks? That's a question. Filter banks will be the way how to efficiently realize the how to efficiently realize actually the linear transforms such as short time Fourier transform and especially wavelet transform. So let's start with it. Maybe I can just jump to something completely different. We can talk about music. I have to share the another screen. Share. Maybe I can share the screen. It's going to be easier. Okay. This is the frequency chart for music, from musical tones, notes, whatever. So take a look at the moment to octave 8. It is the rightmost octave on the piano. Can you
Excuse
see
me. No, I only see a black screen. I don't know if it's just me.
Screen. Okay.
Yes, me too.
Okay, I'm gonna change it to share application. Okay, how about now? Can you see the web page?
Yes.
Okay, so right here we have a table of music notes, music tones for different octaves. If you just imagine a piano for a moment, so you have several, you have a keyboard and several octaves in front of you that repeat itself. So on the rightmost octave is probably octave 8. Maybe you have even 9. It would start at 8 kilohertz and end up at 16 kilohertz. But probably most of the pianists and like here on the screen on octave 8. Let us take a look about the frequencies. Approximately, octave 8 starts about at 4 kilohertz and ends at 8 kilohertz approximately. So the width of the whole octave is 4 kilohertz. Okay, take a look on remaining octaves. Here it's approximately 4 kilohertz, and this is approximately 0, we can say. So the remaining octaves from 7, 6, 5, 4 up to 0, altogether they cover the range of 4 kilohertz. So the rightmost octave covers the same frequency range as the remaining ones on the left-hand side. It stands even for the octave 7 as well, or all other octaves. Octave 7, the range of frequencies is approximately 2 kilohertz. And is it okay? Because I just got the message that our session ended up. But you are still here. Can you hear me?
Yeah, I can still hear you.
Yeah. Okay. I don't know what happened. It was some bad message. Okay, so if you still imagine your piano, so the rightmost octave covers the frequency range as all the others on the left-hand side, and so on. So octave 7 covers the frequency range of 0 to 6 octaves. Octave 6 covers the frequency range of all the leftmost octaves all together. Good. So this is something that actually corresponds to the logarithmic frequency scale. and corresponds to the properties of the wavelet transform. So I will just stop sharing for a moment and change the camera. So if we recall how it looks like, so the discrete wavelet transform was given with something like this. It was some regularization part. Then we had that integral form, and we had two functions. The first one was the input signal, like my voice, your voice, or any biomedical signal, whatever you want. And then we had a wavelet, a small wave, that was actually scaled and then shifted to the left or to the right. The shifts were actually adapted to the scale. The scale could be any positive real number. But for example, for music analysis, it could be the 12th root of 2. Uh, if we don't need such a dense resolution, we can go, for example, through octaves. And if we choose the number 2 uh, as our base scale, then we have actually octave division or in the frequency or scale domain. So it would look like this. It is very widely used. I mean, it's not good enough for music analysis, but it is good enough for compression, for feature extraction or something similar. So it is very widely used. So many people think that this is the definition of the discrete wavelet transform, but it is actually octave discrete wavelet transform. And discrete wavelet transform is more than that. So you can choose any positive number as a as the basis for your scale. Actually, the scales are logarithmic, and the step in the time domain is in this way it corresponds to actually to the scale. So we have a non-uniform division of the time frequency plane. Okay, so let's go back to our slides. So if we are talking about octave uh, discrete wavelet transform, we can see actually the correspondence to a filter bank. Like we can imagine that H1 is a high pass filter that corresponds to the uppermost octave on the piano. So here at the output of such a filter, we have all frequencies together, all 12 halftones that corresponds to the uppermost octave of the piano. And the low pass filter actually corresponds to all other octaves altogether from 0 to 7. Okay, then we need to split it again in two parts, high pass and low pass. And high pass filtering here corresponds to the next octave. I mean, to the octave 7 on the piano, and then to the octave 6, and so on. These switches illustrates discretization. So we are taking samples very fast right here. So on the on the high frequency side, we have a very fast sampling. And if we are talking about octave discrete wavelet transform, then we need slower sampling here, 2 times slower sampling, 2 times slower sampling, then 4 times slower sampling, and so on. So such a thing corresponds to octave DVT. Notice that that here we have continuous filters, which means analog filters. But still, we can see that it consists of a cascade of two-band filters. That brings us to the idea that probably we can use, instead of continuous filters, maybe we can use some discrete filters, also two-band filters. And if you have two filters in a bank, we call it two-band filter bank. So from now on, we will be talking about discrete filters. Of course, it will take some time that we come back to the discrete wavelet transform. So this lecture and the lecture after that, and maybe the one more, we will be talking about discrete filters and discrete filter banks. And then we will come back to the wavelets. So our goal is to achieve an efficient way how to implement the octave discrete wavelet transform. Of course, it is possible, and that is why we are talking about it. And it is widely used in many compression applications, like in compression of human voice, in compression of images, especially digital cinema, and also extraction of features, which is very important, for example, in artificial intelligence systems. In artificial intelligence systems, such a structure remind us to convolutional neural networks that are very popular in analysis of images, object recognition, and so on. So let's start with something extremely simple. So instead of continuous filters, let's talk about two discrete filters. Discrete filters are pieces of software, something that works. I mean, our input signal is a sequence of numbers, and our filters are some very simple structures, or doesn't have to be simple, but some structures that can be realized like a piece of software. Okay, on the left-hand side, you can see how it looks in time domain. So the filters are determined by its impulse response, or they can be described by its Z transform, like transfer function. If Z is equal to e to the power of j omega, we are talking about frequency response. So these are the ways how you can describe a simple discrete filter. Okay, our goal is to use this or something similar to efficiently implement, for example, the short time Fourier transform or discrete wavelet transform. So let's start from some very simple examples. If we are going to use something, the question is, if our filter bank has two filters, the question is whether the information is preserved or not. And the best answer is the information is preserved if the perfect reconstruction is possible. So on the left-hand side, we can see two filters in the back. It is mostly named as analysis part of the filter bank, or analysis filter bank. So we are actually splitting our original sequence of numbers into two sequences of numbers for some reason, to see better, to see some more precise features of the input phenomenon. Okay, we will call it, this is in the middle, this is the transform domain. We will call it mostly image. I mean, it's not an image like a picture or something like that, but it is the image, like we are using different glasses for a deeper insight into the analyzed signal. And then on the right-hand side, we do some reconstruction. So this is the reconstruction part, synthesis part. This is the other name. And we also have, in this case, two filters in the bank. We are collecting information together and reconstructing the original sequence. We can say that the sequence is perfectly reconstructed, even if it has some delay in it. So it is something that we expect of real systems. So we expect that we will be able to reconstruct it perfectly, but also filters introduce some delay. So of course, everything has some sense if the filters in the bank are different, I mean, between each other. Okay, so let's start and see, is it possible or not? Um, let's make an example. So let our filters be as simple as possible. So if we if we want to call some structure a filter, it must have a impulse response of the length at least 2. I mean, if it's 1, it is only an amplifier. So if we have at least 2 samples of the impulse response, we can say that we have filters. So there are no the simplest possible filters have the impulse response of 2. Let all 4 of them have impulse response 2. So let us see what is going on. To achieve the perfect reconstruction, the output must be the same as input, eventually delayed. So delay in z domain is multiplying by z to the power of minus l. Maybe the question: are you familiar with z transform? Have you ever heard of it?
Yes.
Okay, how about the others?
Yes, me too.
Yes,
And me too.
Oh, okay, that's fine. So I can just go on. Okay, so at the very beginning, so we will just say they have 2 sample impulse responses, and these are some numbers in general. We don't know which numbers, but here is one number and the other. So these 2 numbers characterize the transfer function of this filter, and so on. All 4 of them have something like this. So let's check it out. What happens when we have such a filter bank with analysis and synthesis part? So we have a cascade of 2 filters, H0 and F0, and H1 and F1. And finally, we have a sum of the 2. So cascade corresponds to multiplication of their Z transforms. And of course, sum, you can see the sum right here. To have the perfect reconstruction, the overall transfer function must be the poor delay. So which means poor shift by 1, or it can be 0, or it can be 2 samples if we have such a short filters. But it is reasonable to choose that the delay is 1, it is exactly in the middle. 0 delay is probably you cannot realize it, and yeah, maybe it's a very good idea. By multiplying these 2 binomials, we are going to get 3 terms right here for the first addend and also for the second addend, and all together it looks like this. So by some collecting together, we have that results. It takes 3 rows. So on the right-hand side, we have only poor delay by -1, which means that the second term, this one, I mean around this plus, must be, I mean, what is in round brackets must be equal to 1. The first term in the first row must be equal to 0, as well as the last term if we want to have the equality. Okay, so let's put it all together. We have 3 equations and 8 unknown parameters. It means that there are zillion of solutions that satisfy such a system. We have a very big freedom of choice, so we can choose almost anything we want. So 8 3 equations and 8 unknown parameters gives a large space of possible solutions. So it is to have the perfect reconstruction, it is pretty trivial in such a system. Okay, so let's choose something. So let H0 be a very simple low-pass filter. Like, I mean, 1 is the simplest possible low-pass filter you can imagine. And let H1 be also the simplest possible high-pass filter, like 1 and -1. Notice that it is simply a difference between the neighboring samples. So simple difference between the neighboring samples corresponds to a very simple high-pass filter, and this is a very simple low-pass filter. So, okay, we have chosen 4 numbers out of 7. And right now, our equations simplify to something like that, but we still have a lot of freedom to choose. Now we have 4 unknowns and 3 equations. So we still have we have freedom of choice of 1 coefficient, or we have something to choose. So one possible solution is something that looks like this: 1/4, 1/4, -1/4, and 1/4. This is again, F0 is again a low pass filter. F1 again is a high pass filter. Pretty similar like the analysis filters, only divided by 4. So it was pretty easy to find 4 filters that have a perfect reconstruction property in such a structure. So better question is what to do to mess the things, which solutions would not result in perfect reconstruction. So let's take a look in the frequency domain. Our filters were 1, 1, 1, -1. If I just change z to e to the power of j omega, I got a frequency response. And the modulus of that frequency response for 1 and other filters is depicted right here. So the blue one corresponds to low pass filter, H0, and the green one corresponds to high pass filter, H1. Notice that, for example, this high pass filter, if you just if the input sequence is, let's say, 1 1 1 1 1, and the output is actually the difference between the 2 neighboring samples, the output is 0. So DC component or constant applied at the input cannot go through the high pass filter. It corresponds to this 0, the 0 of the green frequency response. It is above the 0 frequency. On contrary, low pass filter like 1 1, if you apply the input sequence, which is actually 1 -1 1 -1 1 -1, and this is the sum of the neighboring samples, okay, then the sum is always 0. So the low pass filter has 2 zeros at the Nyquist frequency, actually at pi and -pi, and such a high frequency cannot go through the low pass filter. So we are talking about zeros of the filters. Zeros of the blue filter and of the green filter do not coincide, which is good, which means that the information, not a single part of information will be missing in the transform domain, in the image domain. That's another name for the transfer domain. Okay, so it was not the miracle. We expect that the perfect reconstruction is possible. So how to make a mess, how to make something the opposite? For example, if 2 filters have coinciding zeros, and this is the example where green one and the blue one have zeros in the same place. So the sequence -1, +1, -1, +1 will not go through either one filter and reconstruction for that frequency will not be possible. So we can say that such a filter bank cannot have a perfect reconstruction property. So altogether, if we have a bank of filters, the zeros are not allowed to coincide. I mean, at least all of the filters in the bank cannot have zeros at the same place, because if they do, there will exist a signal that will not pass through the filter bank. I mean, some of the filters can have zeros, but not all of them at the same place. And there is another catch. If the filters have poles, if they have infinite response, it is not allowed if they have infinite response at the unit circle. So in that case, let's say the finite energy signal will be transformed into the infinite energy image, and in both cases, reconstruction is not possible. Such a simple thing will bring us to the actually theory of frames. We were talking about it. We were just mentioning that there exists some kind of frame theory. We will not go into the details, but we can just take a look. Energy of the signal is right here. So this is the way how to calculate the energy of a discrete signal, of a sequence of numbers. So it is a poor sum of the squared modulus of the samples. Okay, now we apply the filter bank. Our filter bank has only two bands, so we have the output of the filter. So let's denote it by y0 and y1. So the energy in the image domain is actually the sum of the two. So if we go to the Fourier domain, Fourier transform is preserving energy, so we can calculate the same numbers in the frequency domain. So then it looks like this. Okay, why is it important? It is important because for each and every frequency, we can calculate what happens with the energy. So actually, the number that show us what happens with the energy for each and every frequency in the frequency domain is is this one. I mean, the second row written in the frequency domain. Actually, this is the image to signal energy ratio for each and every frequency. So let's check it out for our two examples. So what is going to happen if we apply the filters 1, 1, 1, minus 1, or the second example was 1, 1, 2, 2. Okay, let's check it out. In our first example, interestingly, the energy of the image is constant. It does not depend on the frequency. It means that we have a uniform filter bank. So the energy in the image domain will be the same as the energy of the original signal. Yeah, nice. For example, Fourier transform had such a property. The transform was unitary. But our second example was terrible. I mean, maybe not terrible, but not satisfactory, because some of the signals of the finite energy are actually transformed into the signal of zero energy. Okay, it was not unitary, but it can be important or not. I mean, there are so many applications where you can apply non-uniform filter banks and they will be fine. Now we can introduce the bounds. So what is the, let A denotes the lower energy bound, and B denotes the upper energy bound. On the left-hand side, we have a unitary filter bank where A equals to B equals to 4. So the energy in the image domain is only multiplied by 4, so nobody cares. You just divide by 4 and you know what is the energy of your signal. On the right-hand side, we can see an unacceptable filter bank, which actually transforms some in the range from 0 to 20. And this is not nice for some signals like the sequence -1, 1. We have said that it goes to, it is actually cancelled and it goes to 0. For many applications, it will be acceptable if A is some positive number greater than 0, B is some positive number which is actually greater or equal to A, but it is not infinite, so it must be finite, so less than infinity. So this is a very simple story about the energy frame of our transform. Okay, so our first example was about the simplest possible filters. H0 was a lousy low-pass filter, H1 was a lousy high-pass filter. This example is kind of opposite. Let's have ideal low-pass and ideal high-pass filters that actually takes a part of the input signal spectrum. So they are kind of half-pass filters. So the band, which goes from 0 to pi, is split in half. The blue filter, the H0 filter, takes ideally the lower half of the frequency range, and the green one takes the upper half. But the consequence, I mean, if we have ideal filters, impulse responses of those filters are of infinite length. Let's check it out. So how to calculate it? So this is in general H0. So in polar way, we split the amplitude and the phase. Okay, nice. Our amplitude of ideal filter is 1 for the frequencies that are actually lower than pi half, and 0 otherwise. Let the phase part be constant phase k omega. In this case, k can be 0 as well. So maybe we can have a 0 phase system at least on the screen. So how to calculate the impulse response? We have to apply the inverse Fourier transform, and after some calculation, what we get is a sinc signal, something sine of x over x, sine of something over something. So how does it look like? It looks like this. I mean, it goes to infinity to the left and to the right. This is only, depicted are only a few of samples around 0 for delay k equals 0. If we had some delay, it would be shifted to the right or to the left, depending on whether we have delay, it is shifted to the right, or we have negative delay, then it would be shifted to the left. And on the right-hand side, you can see the ideal frequency response of such a filter. Okay, nice. How about the other one? I mean, the other one is actually, this curve is actually shifted low pass, but shifted by pi. So shifting by pi in frequency domain corresponds to multiplication with e to the j pi n in the time domain. This is the same as cosine, but more precisely, this is the same as the sequence -1 to the power of n, which means reverse every second sample must reverse its sign. So we have actually this. I will just go back for a second. This is the impulse response of the low pass filter, and the impulse response of the ideal high pass filter will be almost the same. Only we have to change the sign of every second sample of the even samples. So it looks like this. So the even samples remain the same of the same sign, and the odd samples change its sign. Okay, so it would be difficult to exactly realize ideal filters, but of course, on our slide, it works fine. So let's make a filter bank that actually consists of two ideal filters. So if we just imagine that our input signal has a spectrum like this, I mean, it is only an example of such a spectrum. Ideal low-pass filter will cut the lower half, ideally. I mean, Y1 is unchanged X, but only up to the frequency pi half. And the ideal high-pass filter cuts out the high-frequency part from pi half to the pi. So this is how it looks like. And actually, if we just apply such a filter bank that consists of two ideal filters, it would be enough to sum the results. So the reconstruction side could be only a piece of wire, I mean, nothing, filters that do nothing, and you just collect the results together. You just add them up and get the original signal. Of course, the pass band of one filter coincides with the stop band of the other, and we have no zero area or zeros that actually coincide between the two filters. So the reconstruction, perfect reconstruction is possible. But okay, it's trivial, only to sum them together, add them up. Okay, let's apply the same filters. Maybe not 100% the same, but let's choose F0, which is actually has the same amplitude response as H0, but the opposite phase. So the phases cancel out. Phases have different signs and amplitude responses are equal. And the same stands for the high pass part. What happens? Nothing special. I mean, if you apply the low pass part, and if you apply it again, but they are both ideals, nothing changes. The same stands for another branch of our filter bank, and you can collect them together to form the original signal. If they have a different signs of the phase responses, such an ideal filter bank would have a delay of 0. If not, if F0 and F1 has the same phase responses as the H0 and H1, then we will introduce some delay, which is also okay for our definition. Okay. Why we are talking about such an ideal filters? Because we can say that we have a dirty plan to change something. I mean, we have just promised that such filter banks will be useful for analysis of the signals, for compression. Okay, for compression. But if you have a sequence of 1,000 numbers right here in image domain, you have 1,000 samples in upper branch and 1,000 samples in lower branch. So instead of 1,000 numbers, now we have 2,000 numbers. It doesn't sound like compression. It sounds that we have more and more data in the image domain. So our idea, such a filter bank is called non-decimated. mapping or transform is obviously redundant. So we have twice as many samples in the image domain. So, but in original octave discrete wavelet transform, we were sampling and we had different sampling rates in different decomposition levels, which bring us to the idea to introduce something that is actually called decimation. Decimation means throwing away every second sample if we have decimation by the factor of 2. If you have decimation by the factor of 10, it means throw away 9 and leave only 1. There is a story that it was something about Roman legions, and one of the way of punishment of that legions was if they did something wrong, to kill every second soldier or something like that in in random order. Or so that's why we are calling that decimation. But to decimate the legion, of course, we will not kill anybody. We are just killing samples of the signal. Decimation of the by factor of 2 means rejecting every second sample. Now, I mean, until now, everything was pretty simple, pretty obvious, pretty simple. We actually did not have to have any serious math. But right now, we have to analyze what happens if you decimate a signal. What does it mean in frequency domain? It means that V is equal to X, but only the even samples. So the question is, what happens in the frequency domain? In time domain, it was pretty simple. So we are going to create a helper signal. The signal actually that has the same number of samples like X, only we are going to put all the odd samples to 0. Let's see how it looks like. On the right-hand side, you can see the pictures. The first one shows actually the signal itself, some example of a signal. Our helper signal U is in the second row, which means that even samples are put to 0. And finally, decimation means that only the even ones live. So only the even ones survived. We just throw away the odd ones. We need that helper signal to develop an equation and to see what happens in the frequency domain. Okay, so what is the spectrum of U? We have to apply the equation. Here it is. But the sum goes only by even ends. It is not a practical way how to express something. We would like to have the same equation as before. The sum goes to each and every even. So we are going to make a trick. So this is the killer trick. So e to the power of minus j omega n is actually equal to the same one when shifted by pi. And when you shift it by pi, it changed the sign. So maybe I can just extend this equation. Okay, this is the idea. Okay, instead of having such a funny sum that goes only by even, we are going to have two sums that goes over all samples. Okay, all samples. The first one is a normal spectrum of our signal, actually. But the second one is shifted spectrum by pi. What is going to happen? odd n terms cancel each other. Even terms add up. So this is the reason why we added 1/2 in front, to have the same value as we had before. So even samples add up, odd samples cancel each other if shifted by pi. And what we have is an exact expression in the Fourier domain for the spectrum of U. So the spectrum of U consists of spectrum of the original signal plus a term that is actually shifted by pi. So that's what happened when you put the zeros every other sample. Since U contains only even samples, we can say that V is U where omega is divided by 2. So you can just divide it by 2, and this is the expression for the spectrum of decimated signal. So we have two effects. One effect is that beside the normal term, we have some, we will call it aliasing term. So the term where the original spectrum is shifted. So you have to add them together. And finally, you have to divide omega by 2 if you want to throw away the odd samples. How does it look like? If we had a spectrum of band, if we have some signal, for example, applied at the input of such a decimator, let's say, in our example, let the signal be band limited to pi/2. Okay, so this is the spectrum of my signal. Of course, we have a discrete system, so actually the spectrum of all discrete signals is periodical. We usually draw only this part, but right here everything is drawn in that picture. Okay, what happens when you divide it by half? When you divide it by half, it looks like this. So it just expanded. So this is C part. Now C part goes from minus pi to plus pi. D part is now right here. B part is right here. Okay. So what happens if you shift it by pi? Okay, you just move it to the right. So B jumps here, C jumps here, and so on. And now you have to add the two components together and multiply by 1/2. This is actually the what happens to our decimated signal. So notice that it was the original one, and this is the spectrum of V. Okay, a lot of mess happened by throwing away every second sample. Okay, this is something that, of course, was expected. But here, the spectrum was band limited to pi/2. What happens if it's not band limited? Then we have some kind of aliasing, so the parts mix together, and we have something like this by decimation. If we want to express the same things in Z domain, then it looks like this. E to the j pi is actually -1, so this is the well-known expression in Z domain. And you have to apply actually the square root power of 1/2 to express the V in Z domain. Okay. So our dirty plan was to use decimation right here. But we also want to design the reconstruction part. At first, here, if you had 1,000 samples right here, you have 5,000 samples here, 5,000 samples here, and of course, you want to reconstruct X all of the 1,000 samples. For that purpose, we are going to use something that is called expander. Actually, it inserts zeros in between the signals. What does it mean? If you have some x of n, I mean, if you have some x of n, you just add zeros in between each and every sample. And in time domain, it looks like this. U equals x, but expanded. So we expanded that, and u, actually that was the way how to create u from v. So, okay, in the frequency domain is pretty trivial because all samples are zero, so you can just put 2 in, and the result is compressed spectrum. Notice that when we decimated the signal, we had expanded spectrum, and now we have compressed. In Z domain is trivial. You have to put Z to the power of 2. So how does it look like if in the upper low the spectrum of some signal is depicted? After inserting zeros, it is narrowed and repeated. So this is what happened. So we have that repeating pattern of spectrum images after inserting zeros. In our filter bank, we are going to have decimation plus expansion. So on the analysis part, we will have decimation. On the analysis part, we will have expansion or inserting zeros. If this is x, this is v, and this is u. Okay, our u, that was our actually helper signal. So we have already shown that the spectrum of u of such a signal looks like this, or in Z domain it looks like this. Oh, now it is much simpler because we don't have to use that part. In the image domain, we will be using actually U, and it looks much better.